Okay, so this is another lecture on isomerism. I think it's the second or the third. And we had ended last time by saying that if a species is devoid of a mirror plane, is devoid of signal, then the species is going to be chiral. Okay? And that a consequence, or not, I guess a definition of chirality, is that the object and the mirror image are not superposable. Okay? And that this essentially then is enantiomerism. So if a molecule does not have a mirror plane that satisfies both the necessary and sufficient condition for chirality, and as far as molecules go, that means that they're going to be enantiomers, that they will exist as one of a pair of enantiomers. The other consequence of being devoid of a mirror plane, and I can draw this arrow either from being devoid of mirror plane or from the chirality, because they go hand in hand, is that the species is optically active, right? Or more correctly, a sample of it is optically active. Okay? And when we say something's optically active, what we mean is that it will rotate plane polarized light. So PPL means plane polarized light. It's plane polarized light. So let's for a minute talk about what plane polarized light is and what it means for the species to rotate it. So light is an electromagnetic phenomenon which we're aware of. It has both electrical and a magnetic component. And light is a transverse wave in the sense that if the light is propagating in this direction, then the direction of oscillation is going to be perpendicular to the direction of propagation. So the vibrations are perpendicular, transverse, if you will, to the direction in which the light beam is passing. But if, for example, I take my eye and I put my eye here and I look at the light beam coming towards me, what I'll actually see then is a point of light, and if I could see the vibrations, they would be in every plane that is perpendicular to that line. Right? And I've drawn 4 of the planes here, 1, 2, 3, 4, but there's an infinite number of planes of vibration, okay, that sort of occur between the limits that I've shown. Well, if I take that light and I pass it into a polarizer, right? For example, a Polaroid lens is an example of a polarizer. What it does, if I put this into a polarizer, right, is that it filters out all the planes of vibrations except for one. Let's say, for example, this plane of vibration, right? And we say light of this type is plane polarized light. Now, one of the consequences of the light being polarized is that you lose a lot of the glare and the images become a lot sharper. So, for example, you find that a lot of fishermen use Polaroid lenses to look down in the ocean, in the water. That way, they're not distracted by the glare off of the water top, so they can actually see the fishes at the bottom. Okay, so that's a trivial use, if you will, of a polarizer. Now, it turns out that polarized light, or plane polarized light as it's called, is able to interact with matter, with molecules. And of course, light interacts with molecules in lots of different ways, right? Light can be absorbed, light can be reflected, light can be refracted, and so on, but by matter. But it turns out that plane polarized light, when it impinges on a molecule, undergoes a rotation. Now, it's important to realize that regardless of what the molecule is, when plane polarized light hits the molecule, then the light undergoes rotation. So let's imagine, for example, I have a molecule of, say, methane. Okay, I've got a molecule of methane. Well, this molecule of methane, let's say I have plane polarized light coming towards the methane molecule in this direction. So the light is coming towards the methane, I'm going to put it this way, in this direction. The light hits the methane. The light will interact with the methane molecule, which is plane polarized, and undergo a rotation. Now, I don't care if the rotation is clockwise or anti-clockwise. Let's say it's 5 degrees clockwise. So it hits the molecule, undergoes a 5-degree clockwise rotation, and continues traveling. But here's the deal. In a sample of methane, right, which means they've got billions of methane molecules, it is a statistical certainty that I will find in the sample a mirror image of this methane molecule. So the light has hit this methane molecule and underwent a 5-degree clockwise rotation. It is going to meet a mirror image of the methane molecule, let's say this one, and that 5-degree clockwise rotation will now undergo a 5-degree anti-clockwise rotation when it hits the mirror image of the first methane. So that light beam is going to be hitting molecules, undergoing a rotation, hitting the mirror image, and then undergoing a corrective rotation. So it'll rotate, correct, rotate, correct, rotate, correct, and then statistically, when the light emerges from the sample of methane, it would have undergone no net rotation. So what we say then is, even though the individual molecule may rotate plane polarized light, a sample of that molecule does not. So we say then that if a molecule has a mirror image, right, that is superposable upon it, in other words, if the molecule is achiral, then a sample of it is not optically active. So it means that achiral compounds, right, so achiral samples, or samples of achiral compounds, right, samples of achiral compounds, right, are not optically active. And the reason is they simply undergo a series of rotations, corrections, rotations, corrections, rotation, corrections. And therefore there's no net rotation at the end. On the other hand, if I take a sample of a particular enantiomer, let's say I take, so these are, obviously this is a tetrahedral site, it's got 4 different groups, so this would be chiral. Here's the mirror image, so these are enantiomers, right? If I take a particular enantiomer, let's say the R compound, and I have a sample of the pure R compound, well, let's say the light impinges upon the molecule, this is plane polarized light, and undergoes a 10-degree rotation that is anti-clockwise. Well, the light will certainly hit other molecules of this compound in other orientations, right, and will undergo other rotations, but it will never meet a mirror image of this compound, because the mirror image of this compound, right, would be the S compound. The mirror image of this molecule is the S compound, and in a pure sample of the R, there is no S, which means all the light will undergo is rotation, 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 never a correction. So when the light comes out of the sample, it would have undergone net rotation. So samples of chiral molecules, right, samples of chiral molecules, right, are optically active. And that's something we said earlier, right, that if a molecule is devoid of sigma, it is going to be chiral. And a consequence of being devoid of sigma, or chirality, is that the species will be optically active. But again, you want to kind of distinguish the optical activity of the individual molecule, which in a sense every single molecule is optically active, versus the optical activity of a sample of the molecules. Because in a sample of an achiral compound, you have no net optical activity. There's no net rotation, so the sample is optically inactive. Okay, now what is the correlation? So how do we define this rotation? And the answer is we define the rotation as alpha. So alpha is referred to as the observed rotation. Right? Alpha is referred as the observed rotation. Right, so alpha then is the observed rotation. And so for example, the way we measure this is with a device called a polarimeter. Right? We use a device called a polarimeter. And a polarimeter is an interesting unit. What I'll describe is the very old version of a polarimeter. And the idea is that you would have a light source, okay, and this light source would, have light rays coming out of it. There would be a slit which would allow only a pencil of light to come through. There would be a monochromator, right, which will select a single frequency of light. And then there would be a tube. Oh, this is a bad diagram already. There would be a tube that would have a sample in it. Okay. Then here there would be a dial. I can't draw this really well, but so what this actually looks like would be something like this. It would be like a circle with a tiny slit in it, and then above it, right, there would be 0, 10, 20, 30 degrees, and then 10, 20, 30 degrees, and this is plus for clockwise and minus for anti-clockwise. Okay, and you would put your eye here. Okay, so when you look, what you'd actually do then is, so you have a light source, right, and usually what's done is use a sodium lamp, right. Then you've got a slit, you've got a monochromator, and the monochromator, as I said, would select only a single frequency, a single color of light, and the frequency of light that's used is called the D line, because when you look at the emission spectrum for an atom, you simply see a series of lines, and if you read left to right, the lines are called A, B, C, and D lines. Right, so the idea then is, so we select the D line of sodium as our reference line, if you will. And what you do initially is you turn this dial so you have your light source on, so there's light passing through. Initially, I'll have some solvent that is not optically active. You know, methanol, hexane, ethyl acetate, doesn't really matter. That's not optically active in my in my cell. And what you'll do is you'll turn the dial so that you're seeing bright, in other words, you're seeing light coming through at 0. Okay? Then what you do is you place your sample into the chamber, right? You've got a sample cell. You place your sample in the chamber, and if your sample is optically active and you look through the slit, you won't see bright anymore, you'll see dark, because the beam of light has been rotated. Well, that would be difficult if you did not use a polarizer, right? So somewhere between the monochromator and the front of the chamber, you would have to use a polarizer. Okay, so you would adjust the polarizer initially. So let's go back over that. You adjust the polarizer initially, so you're seeing bright at 0 when there's no sample, or when there's an achiral sample in the cell. Then you'll put your chiral material in, or your suspected chiral material in, and when you look, you'll see dark. So what you're going to do then is you're going to turn the dial left or right until you see bright again. And if you turn the dial to the right, let's say, or clockwise, and you see bright again at 40, then you would say that the alpha is equal to plus 40 degrees. Right? That's how you use a polarizer. So again, I have my light source, which is a sodium lamp. I've got a slit, which selects a pencil of light, a monochromator, which selects the D line. You've got a polarizer, which you can adjust, right, to decide which plane of vibration you want. You have your cell, and you adjust your polarizer so you see bright through the slit 0. You put in your material and you look through your slit. If you see nothing, well then there's no rotation. But if you see light again, then there's no rotation. But if you see dark, you turn the dial until you see bright again, and if you turn it clockwise by 40 degrees, then it's plus 40. So we say the sample then would be potentially dextro rotatory, right? In other words, it would rotate light to the right. So dextro means right, rotatory means the direction of rotation. But here's the problem. The problem is, well, I can argue, suppose I started turning counterclockwise. And I turned and 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 came here. I could argue that my sample really is not plus 40, but the alpha value really is minus 320. And in fact, my sample is levorotatory. Right? So the sample rotates light clockwise, it's dextrorotatory or plus rotatory. If the sample rotates light anti-clockwise, we say it's levorotatory or it's minus rotatory. It rotates light anti-clockwise. And the question is, how do I know which one it is? How do I know whether my sample is levo or dextro? And as we've seen a little while, it makes a huge difference which one it is. And the answer is really quite simple, and it goes back to the concept of what does alpha, which is the observed rotation, depend upon? Right? Well, what does alpha depend upon? Well, if I think about it, alpha is the rotation suffered by the plane polarized light after it impinges upon upon chiral molecules, right? So the question is, obviously, the more chiral molecules that the light beam encounters, the more rotation it's going to suffer. So I can say then alpha depends simply upon the number of molecules that the light beam enters. Well, what factors affect that? And the answer is, it's affected by the concentration of the sample, and the concentration would be in grams per mil, which actually is in density units. It's affected by the path length of the cell. In other words, how long the cell is. I mean, if my cell is this long, well, then there'll be a few molecules in it. But if at the same concentration my cell is this long, well, then my light beam is going to encounter a lot more molecules. And then, if alpha then depends upon C and L, then I can write, I mean, if I write, for example, that y, if I write y is proportional to x, I can write from that y is equal to some constant, let's say m times x. So if alpha depends upon C and L, right, concentration and path length, I can write from this that y is, not y, I can write that alpha is equal to some constant, which we're going to call the alpha Td times C times L, right, this equation. Now let's define these terms. Alpha is the observed rotation. C is the concentration in grams per mil, really odd unit. L is the path length. L is the path length in decimeters. And L really is a standard unit of 1 decimeter, and that's typically what the cells are made of. This term, the alpha Td, is called the specific rotation. And the specific rotation is unique to a chiral compound. It is as unique to a chiral compound as is the melting point. So in fact, if I isolate a chiral compound, I will report its melting point, its boiling point. If it's a liquid, I'll report its density. I'll also report its alpha Td value. So T here refers to the temperature in degrees Celsius, and D just indicates that it's the D line of sodium. So it's my reference line of sodium. So for example, I can say that a sample has an alpha value, or let's say an alpha 25D of plus 30 degrees. And what does that mean? It means that the specific rotation at 25 degrees Celsius is plus 30 degrees. Okay? That would imply, for example, that if I ran the sample at 25 degrees Celsius using the D line of sodium at a concentration of 1 gram per mil in a cell of 1 decimeter, the observed rotation will be plus 30. Right? If this is plus 30 and I made each of these unit, then the observed rotation will be 30. Now on the other hand, if I made my sample have a concentration of, say, 2 grams per mil, and the path length was 1 decimeter, and my alpha Td was still plus 30, then the alpha is going to be plus 60. So the alpha value, the observed rotation, can vary with the concentration and the path length, which is normally kept constant. but the alpha TD value is a constant at a given temperature. This is a constant, okay, that is unique to the compound. But that then gives us a hint as to how to solve our earlier problem, which is my sample plus 40 degrees or minus 320? And the answer is really very simple. So I had a sample that I ran initially, and I turned my dial to the right and I got a bright at plus 40. But somebody else next to me is doing the same experiment, and their instinct is to go counterclockwise, and they get minus 320. Who is right? Here's what we'll do. We know that alpha is equal to alpha TD CL. So that's a constant, right? And in a given polarimeter, that's a constant. And as I said, in most polarimeters, L is a constant. So it means alpha depends upon, that looks weird, alpha depends upon, linearly upon the concentration. So all I'm going to do is I'm going to take my sample and divide its concentration by a factor of 2. In other words, I will make it half as concentrated, and then I'm going to rerun it in the polarimeter. So if I make it half as concentrated, right, basically sort of doubling the volume, by adding solvent, what I'll find is that if it were plus 40, the alpha value will now drop to plus 20. In other words, my new bright spot will be here. But if it were minus 320, then my new bright spot will now be at minus 160, right? And minus 160 would be somewhere here. So I would actually run 2 experiments. I'd run the first one, okay, and then I'd run a second to decide whether my sample really is levo or dextro. So you run 2 experiments, one at a certain concentration, and then one, pretty easily at half concentration, and we can pinpoint the alpha value for a compound, okay? And obviously, if I know the alpha value, right, if I know alpha, right, and I know my concentration, and I know the path length, then I can write the alpha TD. So the alpha TD would be equal to the observed rotation over the concentration times the path length. So I could determine this for my compound. All right. Now, so it's important to realize that for a given stereoisomer, for a given enantiomer, the alpha value can change because the concentration can change. What is a constant at a given temperature is the alpha TD. Okay? So the specific rotation is constant for a given substance, but the alpha value can vary because the concentration varies. So as I said, it's possible for a compound that has an alpha 25D of, say, plus 30 degrees to show an alpha, right, of plus 30 if we had a unit concentration in a cell of unit path length. It can show plus 15 if, for example, my concentration was halved. It could show plus 90 if my concentration was 3 times the value. It was 3 grams per mil or whatever. What it can never be is negative, right? Because if we're dealing with the plus rotatory enantiomer, the value will always be positive. The observed rotation will always be positive. If it is the levo rotatory enantiomer, then the alpha value will always be negative. But alpha can vary, right, depending upon the concentration, right? So here C is equal to 1, here it's 0.5, here it's equal to 3, right, grams per mil, right, grams per cm cubed. All right, so 2 points about the alpha TD. One is that if I'm dealing with a given pair of enantiomers, so for example, if I'm dealing with this compound, let's say D, and I'm dealing with its enantiomer, which is this compound, right, D and OH, and I don't know offhand, but let's say this compound had an alpha, say 15D, right, of plus 21 degrees. I know that the alpha 15D of this compound is going to be minus 21 degrees. In other words, the specific rotations of the enantiomers have the same number but different signs. Okay, it'll have the same number but different signs. Now understand, I could run the plus and minus compounds, right? Or in this case, the R and S compounds. And I can find that the alpha of the plus compound might be, say, plus 21. But the alpha of the minus compound might be minus 10.5. That's perfectly legal. All it means is one compound was at unit concentration, whereas the other one was half that concentration. Okay? So the specific rotations of the enantiomers have opposite signs but the same value. That's issue number 1. Issue number 2 is, as I change the temperature, the specific rotation will change as well. But I have no idea how they change. Right? In other words, the value can go, in other words, the alpha 15 is plus 21. Maybe the alpha 25, right? This now might be plus 23 or plus 27 or plus 16. I have no idea how the value changes. So I do know that the alpha value or the alpha TD value changes with temperature. I just do not know how it changes. Okay? So if I tell you the alpha 15D is plus 21, what is the alpha 30D? Right? Because I've multiplied this by, I multiplied the temperature by 2. The answer is you have no idea. You know it's plus something, but you just don't know what the something is. Now, the third point is the following. If I look at this compound, this is first priority, second priority, third priority. So this, in fact, is the R compound. This is the R enantiomer. So does the R enantiomer, right, where we are rotating, we are going from first to second to third in a clockwise direction, does the configuration of this site have any bearing on the direction of rotation of plane polarized light? And the answer is none whatsoever. We have made up priorities, right, for these groups, and we've done this arbitrarily, right? And we've said this in that direction would be the R configuration. That's fine. The molecule will rotate plane polarized light as it sees fit. And not because this is R does it mean that this is going to be plus. The configuration of my stereocenter has absolutely no bearing on the direction of rotation of plane polarized light. None whatsoever. However, if the R compound is levorotatory, then I can say the S compound is dextrorotatory. So while there is no link between configuration and direction of rotation of plane polarized light a priori, once I know the relationship between R and the direction of rotation of plane polarized light, then I know what the S enantiomer is going to be. The other issue is, if I look at a compound that has multiple stereocenters, right? That has multiple stereocenters, so OH, D, O, methyl, Cl, and so on, right? These stereocenters have different configurations, right? This is first, second, third. Oh, this is methyl. Let's make this H. So first, second, third. It looks as if I'm going R, but it really is S. This is, let's see, this is chlorine. So this is first, second, third. I'm going this way. So this is R. And this is first, so this is first, second, and third. Well, let's just do one then. So what I have here is first, second, third, and 4 is in the plane of the page, which is where I don't want it. So I'm going to do 2 swaps, and I'm going to end up with 4 here and 2 here, and then 3 here and 1 here. So going from 1 to 2 to 3, this is S, so this is the S. This compound, even though it has 3 stereocenters, and so it's the SRS compound, this compound only rotates plane polarized light in a certain direction. In other words, this doesn't rotate clockwise, and that doesn't rotate anti-clockwise, and that nonsense. The molecule rotates plane polarized light in one direction or the other. So the rotation of plane polarized light is not a feature of a stereocenter, it's a feature of the molecule. And the SRS compound may be plus rotatory, heck, it could be minus rotatory. I have no indication of that information whatsoever. However, if the SRS compound just happens to be, say, plus, then I know its enantiomer, which is the RSR compound, will be minus. Now, what about So the SRS, let's just do this quick analysis. The SRS we know is plus. Therefore, I can say the RSR is going to be minus. These are enantiomers. What if instead I looked at the diastereomer and I asked, well, what about the SSS? And the answer is, I have absolutely no idea. I don't know if the SSS is plus or minus. But let's say somebody did the experiment and they found the SSS was in fact plus. Then I can say the RRR is going to be minus. Okay? Alright, so what we want to do then is switch focus a little bit and look at two terms that we will need to define and utilize. And those terms are enantiomeric excess. Okay, those terms are enantiomeric excess, which is abbreviated EE, and something called optical purity. Which is given the abbreviation OP. So let's see exactly how this comes into play. So suppose then I have a mixture. Suppose I have two enantiomers, right? And let's say I've got enantiomer 1, let's call it A, and enantiomer B. And let's say that the alpha 25D of A is plus 15, and therefore that of B is going to be minus 15, because they're enantiomers. I have a sample, okay, of A and B at a concentration of 1 gram per mil in a cell of path length 1 decimeter. What this means then is that if my mixture is 100% B, then the alpha value that I observe is going to be minus 15 degrees. Now, if it is 100% A, then the alpha value is going to be plus 15 degrees. Now, I recognize, by the way, that if it is 50-50, the alpha value is going to be 0. And of course it will, because I'll have just enough of the lever rotatory enantiomer to counterbalance all of the dextro rotatory enantiomer. And by the way, such a mixture that contains equimolar amounts, of the enantiomers, is called a racemic mixture or a racemate. So I can pretty much say that, if we're pure B, it's minus 15. If we're pure A, we're plus 15. If we're 50-50, the alpha value is 0. But what happens when I'm somewhere, in this region? How do I account for the population distribution if my alpha value is plus 10? Right? Or if I knew I had a ratio of 3 to 1, A to B, how would I figure out what my sample is going to be? Whether it's going to be, plus or minus, and if it is, how much of it? And the way we do that is as follows. So let's answer part of the second question first. Let's say I had a mixture that had 3 parts of A and 1 part B. In other words, I have A, and then B. Now, I could assume, in sort of a way, that this AB represents a racemic mixture. And therefore this unit would have an alpha value of 0. They would cancel each other out. But because I have an excess of the plus rotatory enantiomer, I would expect my mixture to be plus rotatory. So the mixture takes on the rotating power, or the rotating direction, of whichever enantiomer is in excess. The mixture takes on the rotating direction of whichever enantiomer is in excess. Okay? Alright, so how do I handle mixtures that are not pure A or pure B or 50-50? And the answer is by the equations, by the terms EE and OP. So EE is defined as a number of moles of the enantiomer that's the major enantiomer, the one in excess, minus a number of moles of the enantiomer that is present in smaller amounts, the minor, over the sum, right? In other words, n major plus n minor times 100. So the EE is written as a percentage. So for example, in the case we just talked about, we had a 3-to-1 ratio of A to B. The EE would be 3, because I've got 3 parts of A, minus 1, over 3 plus 1 times 100. So that's going to give you a 50% EE. Right? So it's 2 over 4 times 100, that's 50%. Now by the way, of course that makes sense, because if you look, I have A, and B. So of the 4 pieces that I have, the 4 parts, 1, 2, 3, 4, this is racemic, and 2 of the 4 represent the enantiomers in excess of the racemic mixture. So obviously this is a 50% enantiomeric excess. Okay? Now the OP is defined as the alpha TD of the mixture over the alpha TD of the pure enantiomer in excess, right? The pure species in excess, or let's just call it the major enantiomer. Okay, the major enantiomer. And the third equation is that the OP and the EE are equivalent numbers. In other words, whereas the EE is written as a percentage, the OP is written as a fraction, or sometimes a decimal. So if I have an EE of 50%, my OP is going to be half, or 0.5. Okay, so the EE and the OP are equivalent. Okay, we're going to stop here, and we will do the last lecture next. All right.